All right, so our last section we're going to look at this week is 2.1. And this part of the section talks a little bit about angles. So we'll start very basic, like what an angle is, and then we'll talk about how we can measure it. There's two ways you can measure angles. Degrees is one of them. I'm going to show you the other way as well. Okay, so that's what's in this first part. So before we even talk about an angle, we're going to talk about what makes up an angle, and that is two different rays. Okay. So if you draw something like that, okay, that's a ray. And then if you put another ray that has the same starting point, like that, now you've created an angle. Okay, so an angle is made up of two rays, and the starting point is called the vertex. Okay, kind of drew all that out for you already, that the ray extends in one direction forever. Okay, and when we are talking about an angle in trig, I guess there's two different ways we can talk about angles. You can talk about an angle that's all by itself, like that, or you can talk about an angle like that's part of a shape. Okay? If you're talking about an angle like that, these two sides of the angle are not rays. Well, what do you call this and this in general? So like this part right here. Just these two pieces. They're not rays, but they are
Jason. Lines.
No, they're not lines either. These are not lines. What are these? Yeah? Segments, yeah. So if you have two segments that have a common point, or you have two rays that have a common point, you have an angle in both cases. Just this is an angle that's all by itself. This is an angle that's part of a shape. Okay? But they're still both angles. Okay, the kind of angle that we're going to be talking about in this section is more the angle that's all by itself. We're not really going to be talking about angles as part of a shape today. Okay, so this is the kind of angle we're talking about. Take two rays, put them together with a common vertex, and now you've created an angle. Okay, and there's another picture of an angle. Each of these rays has a name, which I'm going to go over in a minute. But any question on the definition of an angle? Two rays with a common starting point. That's pretty much it. Okay. So we're going to name each side of that angle. Okay, this side is called the initial side. And the other side is called the terminal side. Right, so the initial side and the terminal side. The way that you know which side is which is if you are standing like right there between the two rays, you rotate counterclockwise. As you rotate counterclockwise, the side that you would start at is the initial. The side where you end is the terminal. Okay. Here's another example. So there's two rays. Stand between them. Rotate counterclockwise. Where you start is the initial. Where you end is the terminal. Now you can take that angle, just group that all together. Okay. Even if you rotate it like that, the labeling is still correct. Right? Go between the two rays, rotate counterclockwise. So the side pointing up and to the right is the initial. The side pointing up and to the left is the terminal. Okay. We generally like to draw the initial side horizontal. So if you were going to draw this angle, rather than have it like turned like that, I would say the best way to draw it would be like that. Okay. generally like the initial side to be nice and flat, okay, horizontal. So any question on which side is which? Initial, and then you rotate counterclockwise to the terminal. Okay. Now, as we rotate, you can rotate in two different directions. Can anybody tell me, what are the two directions if you're rotating on a circle that you can go? Yeah?
Clockwise and counterclockwise.
Right, we can go clockwise and counterclockwise. And the difference between rotating clockwise and counterclockwise is basically what kind of angle you have. It's just a different direction, right? If you rotate counterclockwise when you're measuring an angle, that would be a positive angle. If you rotate clockwise when you're measuring an angle, okay, that would be a negative angle. And I'll show you guys an example of that. Okay, so having positive and negative angles, that doesn't really apply to a shape. All right? When you draw a triangle, there's no such thing as a negative angle in a triangle. They're all positive. Where you see negative and positive angles kind of start to come in is in a picture like this. If you're on a circle and you rotate a certain amount, because I rotated counterclockwise, it shows me the angle is a positive number. All I can do here is move the terminal side. I can't move the initial side. That always stays horizontal. But if I rotate in the other direction, okay, look what happens to my angle. Because I went clockwise, it's showing as a negative angle. Okay? So that's the only difference between a positive angle and a negative angle. It's describing the direction you rotated in. Okay? And if you keep rotating, if you went all the way around, does anybody know how many degrees to go all the way around? Yep.
360.
Yep, 360. I'm going in the clockwise direction. That's why you see a negative. So if I go all the way to 360, it shows me that's one full rotation. And then if I keep going, now I have more than one rotation. So you can get angles that are bigger and smaller than 360 when you are rotating. Okay. Would you have an angle like that in a triangle? No. It's too big for a triangle. Right. Same thing in the positive direction. If I keep rotating in the counterclockwise, eventually I'll go all the way around. I'll get 360. And if I keep going, it gets to be more than 360. Now you'll notice there's another number down below. Okay, the top number has the little circle next to it, so it's measuring in degrees. The bottom number, we're going to talk about that in a little bit. Okay, that's a different number. Does anybody know what the unit is for that bottom number? It's not degrees. Yeah?
Is it radians?
It is radians. And you'll notice that some of these numbers, if you get on just the right one, all of a sudden it changes to a number with pi, right? So like 45 would probably show one with pi, and then 60 would, yep, all of a sudden it changes 30, probably be another one. So radians has a lot to do with pi. Okay, so we're going to talk about that. All right, so any question on the difference between a positive and a negative angle? It's just the direction. Okay, so I told you that when we draw an angle, we like the initial side to be a certain way. This, if you're going to draw a 90-degree angle, and you did something like that, even though that is a 90-degree angle, that's not generally how we would draw it. Okay, we would want to draw it like that. Okay. Drawing a 90-degree angle like that is called standard position. Okay. Two things have to happen for an angle to be in standard position. One, if you had like an XY coordinate or graph paper, you want the vertex at the origin. Just like that. The second thing that you want is you want the initial side to be on the x-axis, okay, specifically the positive x-axis. So vertex at the origin, initial side on the positive x-axis. That's called standard position. Okay, what that does for us is if I asked you to sketch a 45-degree angle, everybody's 45-degree angle would be oriented the same way. Okay. If I didn't say standard position, I mean, some people might draw it like that, some people might draw it like that. People might draw it all different ways. But standard position is only one way. All right. What if I did that? Is that angle still in standard position?
No,
No, what's wrong with that?
it's not on the origin.
Right, the vertex isn't at the origin. Okay. The initial side is on the positive x-axis, but it has to be both. Okay. How about if I did something like this? Is that standard position?
No,
No. What's wrong now?
it's not on the x-axis.
Right, the initial side is not on the x-axis. The terminal side is on the y-axis, but that's not part of the definition at all. Okay. So standard position has to look just like that. Okay. Any question on what it means to draw an angle in standard position? Okay. All right, so let's take a look now at two different ways that we can measure an angle. Okay, one way we talked about, I've kind of shown you a little bit, is degrees. Now we're going to look at another way called radians. I think we already said this, but what's the connection between an entire revolution and degrees? How many? 360. Okay, there's 360 degrees in one revolution. What I want to figure out is the question mark. How many radians in one revolution? Now, once you know some kind of fact between two different units, you can use that fact to convert between the two. So let's say we know in one revolution there are 360 degrees. I want to figure out how much 210 degrees is in revolutions. Well, all I have to do is set up a proportion like that. One side of the proportion has to be something that I know is true. Is that the only fact that's true between degrees and revolutions? No. You could do, for example, if you did 0.5 revolutions, how many degrees in 0.5 revolutions? Yeah. 180. Yeah. Right. Just like saying in 12 inches is a foot. Is that the only fact that connects feet and inches? No. You could say 2 feet is 24 inches. 3 feet is 36. You just need something true on one side. And then on the other side, you can put what you're trying to figure out. So now if you cross multiply, you'd end up with 210 equals 360x. If you divide each side by 360, that would tell you exactly how much of a revolution 210 degrees is. It's a little over half a revolution, about 0.58. Right. So I'm not really as interested in converting between degrees and revolutions. I'm more interested in getting between degrees and radians. So what I'm going to do is we're going to eventually figure out what that question mark is. But I'm going to start just by describing to you what a radian looks like. Okay, I'm going to give you kind of a visual that you can look at to understand what it is. Now, if you look at the word radian, does it have another word that's in it that sometimes we see in geometry? It looks kind of similar to this word. Radius, yes. So radians, radius, they have a lot to do with each other. All right, so let's draw that picture. Okay, what I've done is I've drawn a circle. And inside that circle, I've put an angle with a vertex right at the center of the circle. From that vertex, I drew two rays. and the rays hit the edge of the circle at those two blue dots. Any questions so far? All right. What I did next is I connected those two blue dots with that red thing that I drew. Does anybody know what that red thing is? It's not a line segment because it's not straight. It's not a ray. It's not a, yeah? It's an arc. Okay, so I created an arc between those two blue dots. Okay. Now, what I'm trying to explain here, that's a pretty good picture. I think that picture is pretty much to scale. If you measure the length of that black line that I just drew, and you measure the length of that red arc that I just drew, and they come out exactly the same, then you have a picture of 1 radian. Okay. So in that picture, if the length of that arc in red is the same length as the radius, then you have a picture of 1 radian. Now, is this length and the arc length always the same? No. If I drew a circle like this, and I drew an angle like that, look at the length of this arc in red, and compare that to the length of the radius of the circle. Do they look the same this time? No. Which one looks bigger? The what? So which one out of the two things we're comparing there, which one looks bigger in that circle? The arc, yeah, the arc is a lot bigger. Okay, the arc, if you took like a piece of string and you measured it, that arc is a lot bigger than that radius. Okay. Likewise, I could also have a circle, draw an angle like this. There's my arc. How does the arc compare to the radius this time?
Small.
Yeah, it's a lot smaller. Okay, the length of the radius is that big. Length of the arc is much smaller. So they don't always have to be the same. But if they are, then what you have a picture of right here is 1 radian. And I'd say that's probably a pretty accurate picture of what a radian looks like. About that big. Okay, so that doesn't really help us to convert between radians and degrees. What it does is it gives you a visual to see what a radian looks like. Okay. Any question on that idea? Okay. And that idea is going to be important for something we do tomorrow. Okay. If the arc length and the radius length are the same, you automatically have 1 radian. That's an important idea. If they're not the same, then you don't have 1 radian. You have something else. All right. So the next thing I'm going to give you is a fact about an angle. To convert between radians and degrees, I got to give you something to start with, right? It's kind of like if I said, to somebody in like preschool to convert between feet and inches, but I didn't tell them anything about feet and inches. Well, how are they going to convert between feet and inches if I don't at least give them like a fact about feet and inches to start with? Okay, so that's what I'm going to give you here. Okay, I'm going to give you a fact that we can build off of. And it says that an angle's measurement in radians is equal to the length of an arc on a very special circle, okay, on the unit circle. So let's start by explaining what a unit circle is. A unit circle is just a circle that has a certain size to it. Does anybody have a guess what the size of the radius is in a unit circle? Yeah? 1. Yep. So a circle with a radius of 1, that is a very special circle that we use in trig, and it is called a unit circle. All right. So what am I saying in that sentence? Okay. Well, let's look at a picture. So let's draw a unit circle. let's say that's circle has a size of 1. It doesn't matter 1 what, 1 foot, 1 inch, 1 centimeter, just 1. Okay, so this is a unit circle. It says if you have an angle, and I need to draw it in this circle. So let me draw an angle in the unit circle. Here is an angle, just like that. Okay, so now I have an angle in the circle. And it says that if we measure the angle in radians, this is the angle in radians from there to there. It's also comparing it to the length of an arc. That's the length of the arc from there to there. What does that sentence say if you compare the size of this angle in radians to the size of this arc in a unit circle? It says that those two things are what?
Of course. Equal.
Equal, yes. They are equal. So what that means is, if, let's say this is in feet. If this is 1.5 radians, when you measure that with like a protractor, then if you took a piece of string, laid it down and measured that, that would come out to 1.5 feet. Right? So if you put a protractor on that and it comes out to 2 radians, then that would come out to 2 feet. If it was 1.6 radians, this would be 1.6 feet. These two things always come out exactly the same on this type of circle. Do they on other circles? No. But on this circle, they do. And it has to be done in radians. So if you measure it in degrees, like if this is 10 degrees, is that going to be 10 feet? No, that doesn't work. But the size of this angle in radians and the length of this arc will always come out exactly the same. Right? So we can use that to figure out how many radians in one full revolution. Right? So let's draw another circle. Okay, let's again pretend that that's a unit circle. I didn't measure it exactly, but let's say that's my unit circle. And let's say that I drew an angle like that. If you want me to kind of break it out, that would be the initial side. That would be the terminal side. How big is that angle? That's a 180 degree angle. Now I know we need to work in radians, but that's okay. We're going to do that. That's a 180 degree angle. How much of the circle does that arc take up? Okay, so 100 degree angle gives you an arc that is half the circle. Okay. All right, let's draw another one. Let's say I draw a circle. Okay, I gotta make it a little smaller. All right, let's say that's my initial side. That's my terminal side. And I'm looking at this angle like that. How big of an angle is that?
270.
That angle's 270. And how much of the circle does that arc take up? That takes up 3/4. So 270 gives you an arc that is 3/4 of the circle. All right, so now let's take it one more step. Draw one more. Let's make a circle. And let's put our initial side here and my terminal side right there. Now I'm looking at that angle. Okay? Not a little bit of a circle, not half a circle, not 3/4 of a circle. This time it's the whole circle. How big would the angle be that takes up the whole circle? It would be 360. So that's a 360 degrees. And this gives you an arc that is the entire circle. And that's going to be the key. We give you this arc. If I can find the length of that arc, I know that the length of that arc is going to be the same as what? What does that sentence say? The length of the arc is the same as? Right. The length of that arc is exactly the same as the measure of that angle in radians. And that's what I want to know. How many radians does it take to go all the way around the circle? So if you can figure out the length of the arc that goes all the way around the circle, it's going to be the same as the size of the angle that goes all the way around the circle in radians. I already know the size of the angle around the circle in degrees, but that's not what I want. I want radians. Okay, so now let's focus on finding the length of this arc. And whatever that comes out to, that is my answer for how many radians to go all the way around the circle, because they're the same. This is an arc that's so big it takes up the whole circle. Does anybody know what we call an arc that goes all the way around the circle? It has a special name. Specifically, the length of the arc going all the way around the circle. Yeah? It's the circumference. So what we want to figure out is the circumference of that circle. That's how many radians to go all the way around. What's the formula for the circumference of a circle? We don't know that, we're stuck.
That's like radius times pi squared, right?
So pi r squared is the area. That is a formula we're going to use tomorrow, I think. Yeah, we'll use that tomorrow. So hang on to that. But we need this one. We need the formula for just the circumference, not the area. Anybody remember circumference of a circle? Anybody have a guess what it involves? Yeah?
Multiplication?
Okay, it does have multiplication. Anything else that it has in it?
Is it diameter radius? Diameter times radius squared.
So pi r squared is for area. You don't square anything when you're finding circumference. Only when you're finding area. Yep.
Are you multiplying the angle? That, like, obviously for 360, like multiplying like the angle times the radius?
When you're finding circumference, you don't need an angle from geometry. No. Formula for circumference doesn't have an angle in there. Anyone else have a guess what it does have in it? Yeah?
Does it involve radius?
Yeah. It does involve the radius, and it involves something else. What's usually involved when you're dealing with like circular or spherical shapes? Pi. So it does have pi in it somewhere. It has the radius and it has a number. Anybody remember?
Squared?
No, nothing squared. Squaring is when you're finding area. Yeah.
Times 1/2?
No, it's not times a half. But there is a pi and an r in it, and there's something else.
Oh,
Yeah?
2?
2. That's the formula for the circumference of a circle. So now, let's find the circumference of our unit circle. What would I fill in for r if I'm using a unit circle? 1. So the circumference of the unit circle is 2 pi times 1. And what is 2 pi times 1?
2 times 3.14.
We're going to leave it in terms of pi. It's just 2 pi, yeah. So the length of the arc that goes all the way around this circle is 2 pi. Remind me again, what did we say the length of the arc is the same as? The length of the arc is the same as the angle measured in
Radians.
radians. So if the length of the arc is 2 pi, then the measure of the angle in radians is also 2 pi. That's how many radians it takes to go all the way around the circle. 2 pi. And I can show you that if I bring this picture back up and I go all the way around the circle. Notice when I get to 360, it says 360 is 2 pi. What if I went in the clockwise direction? What would one full revolution be going clockwise in radians? Yeah?
Negative 2 pi.
Yeah, it would be negative 2 pi. There we go. Negative 2 pi. So 2 pi is how many radians it takes to go all the way around the circle. All right, now that we know this, we can come up with a formula to convert between degrees and radians because we have a true fact. Is it the only true fact? No. In fact, we're going to simplify that a little bit. Okay, so 360 degrees equals 2 pi radians. Let's divide each side by 2 and just get a little bit reduced fact. If I divide each side by 2, what do I get?
180 equals 1 pi.
Yeah, 180 degrees equals pi radians. So that's a little bit simpler fact. We made the numbers a little smaller. Okay, and I can show you that just by going on here. If I go halfway around, 180 degrees is pi radians. Now, those are both true facts, but normally when you give someone a fact to convert from one thing to another, you usually have a certain number in there. Not a 180, not a pi, not a 360, not a 2 pi. What number do you usually tell somebody when you give them a conversion between this and that? Think if you had to explain any conversion to somebody. Think of the conversion you would tell them in your head, and then tell me what number is in that conversion. There's a common number in every conversion if you want to make it simple for someone to understand how to convert between two things. Right? Like I could tell you there are 120 inches in 10 feet, but I could have made life a lot easier for you. Right? That's not the easiest way for me to explain it. Yep? 1. When you give someone a conversion, usually it has the number 1. Like if you're going to say how many minutes in an hour, you'd say 60 minutes in an hour. You don't normally tell somebody there's 180 minutes in 3 hours. I mean, that's true, but it's more complicated than it needs to be. So let's see if we can look at this, and let's introduce a 1 into that formula. Let's get a 1 on this side. What could I do arithmetic-wise to turn that into a 1? And then I'll do the same thing on that side. How can we turn 180 into 1? Just with one arithmetic operation. Either add, subtract, multiply, or divide.
Divide 180.
Yeah. Let's divide each side by 180. If we do that, we get the formula 1 degree equals pi divided by 180 radians. 1 degree equals pi divided by 180 radians. Now, if I wanted a formula for 2 degrees, very easy. I can take that fact, which I know is true, and all I have to do is multiply each side by 2. Now I have a formula for 2 degrees. What if I wanted a formula for 5 degrees? Times each side by 5. Now the left side is 5 degrees, and the right side is in radians, 5 pi over 180. It's not important what you put in the blue box. What's important is what you do to the number in the blue box. You're multiplying it by pi, and you're dividing it by 180. So anytime that you want to convert from degrees to radians, basically put whatever number you want to convert in the blue box. You want to convert 13? Okay, put a 13 in that box. Multiply the number in that box by pi, and then divide that by 180. That's the process to convert from a degree to a radian. And it doesn't matter what you're converting. That's the process for any number you want to convert. Multiply by pi, divide by 180. Okay. Now let's go back to the formula we started with. And last time we got a 1 on the left. This time, let's get a 1 on the right. And that's going to convert the other way. How would I get a 1 on the right side here? Yep, we divide by pi. And divide by pi. If you do that, you're going to get a formula with a 1 in it. 1 radian equals 180 degrees over pi. So that is exactly what 1 radian is. If you did that out on your calculator, 180 divided by pi, I think it's about 57 something. All right. So now, let's say instead of I want to convert 1 radian, I want to convert 2 radians to degrees. What would I multiply each side by? 2. Multiply by 2. Multiply by 2. And now it says 2 radians equals, and you've got a calculation you can do. What if I wanted to convert 5 radians to degrees? I would plug in a 5 into the blue box. Again, the number that you're plugging in to the box, that's not the important part. This is the important part right here. You're multiplying the number in the blue box by what? No, the number, whatever number is in that box. You're multiplying it by 180, and then you're dividing it by pi. Those are the 2 steps to convert from a radian to a degree. You multiply by 180, divide by pi. Multiply by 180, divide by pi. All right, so the 2 steps are very similar. So they can be kind of easy to mix up. Multiply by pi, divide by 180. Multiply by 180, divide by pi. So I'm going to give you a way that you can kind of remember it. Whenever I say degrees, okay, the number that I want you to connect with degrees is 180, because 180 has a degree symbol on it. Okay, so when I say degrees, think 180. Degrees, think 180. When I say pi, I want you to think radians, because pi has the word RAD after it. So pi, radians. Kind of connect those 2 thoughts in your head. Radians goes with pi, degrees goes with 180. If you can remember those 2 things, then all of that becomes automatic. All right. So now let's finish up by converting a few problems to degrees to radians. We're going to do some where we leave the answer exact with a pi in it. And then we'll also do some where we round to 2 decimal places. So let's start with 60 degrees. The directions are to convert 60 degrees to radians. First thing we might want to do is just to think of it as a fraction. Just put it over 1. Because you're going to multiply this by one of 2 things. You're either going to multiply by pi over 180 or 180 over pi. It's going to be one of those 2. Look where degrees is in that fraction. We're trying to get the degrees to cancel. When we're done, we don't want degrees, we want radians. Where would degrees have to go in the second fraction to cancel out degrees in the first fraction? Yeah. It would have to go in the bottom. If degrees is going to go in the bottom, what's the other unit that has to go in the top? The unit. Well, that's a number. Yeah. What is it? Radians. Okay, so if degrees is in the top, degrees is in the bottom, that will cancel that, and that means radians is in the top. Now we just need to write down what number is connected with each one of those. What number did I say to always think of when you see the degree symbol, when you're converting like this? Yep, so that's going to be the 180. And when we're converting, what number did I say to think of when you see the radian? Pi. Okay, now we just do that out, and that's our answer. Generally, before you multiply, you want to reduce as much as you can. What's the biggest number that goes into 60 and 180? 60. How many times does 60 go into 60? Once. How many times does it go into 180?
3 times.
3 times. So the answer that we get is 1 times pi. And in the bottom, 1 times 3. That's how you write your final answer. What does it look like? I might have forgot to write down, but I didn't forget to write it down. Radians. Okay. We have to get used to not seeing RAD. When something is in radians, notice they do not put RAD after it. There is no label. So then how do you know if you're working in radians or degrees? Well, if you're in degrees, you're going to see the little circle. If you're talking about an angle and there's no little circle on it, then it is automatically radians. So from now on, I'm no longer going to put RAD after radians because you don't do that. Okay? And that's showing you that what we did is correct. 60 degrees is pi over 3 radians. If you're wondering which numbers here is it going to show pi's for, and then which ones does it do decimals for, generally anything that's a multiple of 30 or 45, it's going to show a pi for it. So like 135, it should. Yep, 3 pi over 4. So multiples of 30 and 45. Just because those are pretty common, and we're gonna do a lot more with like 30s and 45s later on in a couple weeks. All right, let's try another one. Let's try 150 degrees. Okay, that is a multiple of 30. It's 30 times 5. So you would be writing an exact answer. On the test, there won't be any confusion. In the directions, I will put convert to radians, leave your answer exact. Okay. No decimal. All right, let's think of it as a fraction. We're converting to radians, so we want degrees to cancel. Where is degrees going to go to cancel out? Bottom. So that means what unit is in the top? Radians. Remember, it's going to be invisible, though. We're not going to write it. What number, when we're converting, do we connect with degrees?
180.
It's the 180. And the number we connect with radians? Pi. And now reduce as much as you can. What number goes into 150 and 180? What number goes into 150 and 180?
30.
30. How many times does 30 go into 150?
5.
5. And into 180? 6. So you're left with 5. Degrees cancels. 5 times pi in the top. And what are you left with in the bottom? 6. And that's your final answer. So let's check 150 degrees and see if it says 5 pi over 6. There you go. 150 degrees is 5 pi over 6. Okay. Any question on that one? All right, let's try a negative. Negative doesn't change how you do anything. It just means your final answer is going to have a negative. If it started negative, it's going to stay negative. If it started positive, it's going to stay positive. The sign can never switch when you're converting. Okay. All right, so we're getting rid of degrees. So what goes in the bottom?
Degrees.
Yep, and what number goes with that?
180.
180 degrees. What goes in the top?
Pi.
Pi radians. I'm going to pretend like we wrote RAD. Degrees in the top and the bottom cancel each other out. What number goes into both 45 and 180?
45.
Yep. 45 goes into itself once. How many times does it go into 180?
4.
4. And what do you get for a final answer?
Pi divided by 4.
Say it again.
Pi divided by 4.
Not pi divided by 4.
45 pi divided by 4.
Yep.
Negative pi over 4.
Negative pi over 4. So don't forget the negative. Okay, negative pi divided by 4. Okay. Any question on that one? Now, this one I want to try a little different. 90. We know negative 45 is negative pi over 4. So what's positive 45?
Pi divided by 4.
Just play with
Pi over 4. Now, I want to get 90, but I know 45. What do you have to do to 45 to make it 90?
Multiply by
You have to multiply it by 2. You just have to double it. So what would you get if you double that?
2. Pi divided by 8.
How about before you reduce it, what would you get? If you double pi over 4, you have
2 pi over 8.
2 pi over 8. No, that's the same thing as pi over 4. What do you get if you double pi over 4? Yep. 2 pi over 4. So all we did that time is we took something we already know and we doubled it because 90 is double 45. And then if you reduce it, what would you end up with?
pi over 2.
Pi over 2. Okay, so when I'm converting between degrees and radians, a lot of times I use other smaller numbers that I have memorized to figure out bigger numbers that I might not have memorized. If there isn't one that I have memorized that's going to help me, then yes, I can go through the whole thing from scratch. But I would say like 95% of the time, I know another number that I can use to figure out a bigger number. Okay. So same with like 60. If they wanted to know 120, I have 60 memorized. I would just double it to get 120. But it takes a little practice to memorize them before you start that. All right, so any questions on finding an exact answer? All right, let's try one where we round. So round to 2 decimal places. So same directions as above. Okay, convert to radians. I'm just adding an extra step here. Round your answer to 2 decimal places. Okay, so we already know what we're going to multiply by. It's the same thing we've been doing every problem. Pi over 180. This time, even if these did reduce, I don't care. Okay? Because I'm going to type that all into the calculator and just see what I get. How do you think I should type in this on the calculator? What should I do to type that in?
You just do 3.14 since you're
Like second and like it's above the division sign.
Yeah, I want to do second, and I want to do it that way. Why do you think I want to do it that way instead of 3.14?
Is this pi?
Yeah, it has more accuracy to it. So anytime you are converting between degrees and radians, if you need to round it and it involves pi, use the pi button. Okay, you also don't need any parentheses there. The calculator will, that's simple enough, the calculator will do PEMDAS correctly. But it's 1.87. Should I put a label on it?
Yeah.
Well, what is the label? Radians. Do I write that? No, you never write radians. So if you put an answer like that on a test and it's a problem about an angle, I know that that's radians because you didn't put the degree. Okay, I'll do one in a minute where if you round that to 3.14, I'll show you how much it throws your answer off. All right, so let's try a couple converting from radians to degrees. Now you have to pretend like it says RAD next to pi. I just erased it on purpose. Okay, so pretend like it says RAD in the top, next to the pi. We're trying to cancel out radians, and I want to end up with degrees. If radians is in the top, on the left, where would radians go in this fraction? Bottom. And what number do we always put with radians? Pi. Okay, if radians is in the bottom, now they're going to cancel. What would go in the top? 180 degrees. Okay, so radians cancels, that's invisible. What else cancels there? The pi's cancel. And now you're left with 180 divided by 6. What's 180 divided by 6? 30. 30. And do I need a label on that?
Degrees.
Yes. If you do not put a label, then that would be 30 radians. That's not what we want. And that's it, 30 degrees. All right, let's try again. Get used to not seeing the word radian. Okay, radians is in the top. So where is the pi going to go in the other fraction?
Bottom.
Goes in the bottom. And what goes in the top? 180 degrees. RAD and RAD cancel, but that's invisible. What else is going to cancel? Pi's. And we can reduce. 2 goes into itself once. How many times does 2 go into 180?
90.
90. Notice I did not cross out the degree sign. That doesn't cancel. Just the 180 canceled. What am I left with for my final answer there?
3 times 90.
3 times 90
Degrees.
degrees. And what's 3 times 90 degrees?
270 degrees.
270 degrees. Okay, so that's how you convert and get an exact answer. Let's finish up with one where we do a decimal. Okay, so this one is 3. So we'll say round to 2 decimal places. So convert to degrees, round to 2 decimal places. Okay, this doesn't have a pi in it. That's fine. Not every radian number has to have a pi in it. That's like just saying, every, number on the calendar has to have a 4 in it. No, there's numbers without 4s. So you don't have to have pi. So that's 3 radians. Okay. What's going to go in the top if I'm converting and trying to get rid of radians? 180 degrees in the top. What's going to go in the bottom? Pi radians. Yep, so it's like RAD, RAD, RADs cancel. Okay, let's type that in. Do it the same way we did it before. Use the pi button. So that's 540 divided by pi, 171.89. And remember, that is in degrees. Okay, now, if you don't use the pi button, the top was what, 540 divided by 3.14. Okay, if I'm looking for you to get an answer that's accurate to 2 decimal places, there's a pretty big difference between 89 and 97. They're not the same number. Okay. So not using the pi button will throw your answer off. Okay. Any questions on that? Okay. So that pretty much covers the first part of 2.1. Okay, so the homework tonight, it's 36 to 68, just the evens. Right? And there's a mixture of all different problems. Okay, some you're converting to degrees, some you're converting to radians, some you're exact answers, some you're doing decimal answers. So you will need a calculator, but I don't think you're going to need a graphing calculator for really much else we do, almost for the rest of the year. You can still use them because those are the ones we've been using and you're comfortable with them. But I don't think you'll need it for most stuff. Just a regular calculator.